there. My name is Heath. This is the first day of Math 3134, which is Applied Combinatorics. Welcome aboard. Um, I'm looking forward to working with you this semester. Let's go ahead and get started. What we're covering today are the addition and multiplication laws. Let's talk about what we mean from that. So, our goal is to be able to count how many outcomes are possible for a described scenario that has multiple possible outputs. And the addition law applies when we're choosing a single object from disjoint sets. And it's easier to see an example than to describe it verbally. So let's look at this example. Suppose we have a box of DVDs and this box contains 3 different comedies, 5 different action films, and I'm going to have to crowd these in, and 2 different horror films. And I reach into the box and pull out 1 DVD. Okay. How many possible outcomes are there? How many choices do I have? Well, it's pretty obvious that there are 10 choices possible. There are 10 different DVDs in the box. I've just described the set of comedies, the set of action films, the set of horror films, but if they're all in the box and I pull 1 DVD out, there are 10 possible outcomes. Okay? Easy example. We'll do some more complicated ones in a moment, but that's the idea. The important thing is that these groupings, comedies, action films, and horror films, did not overlap. We were not double counting any movies in the process. And we call that disjoint sets. If we have a set of sets, we say that they are disjoint sets if no matter which 2 sets we pick in this group, the intersection of those 2 sets is the empty set. Okay? So we say these sets are disjoint if no element is in more than 1 set. And if we have disjoint finite sets, then the number of ways of choosing one object from the union of those sets is the number of elements in S1 plus the number of elements in S2 plus so on and so forth, where the absolute values in this case denote the number of elements in the set X. Okay? This is in the book, and this is Theorem 2.11, but it is the first principle we're going to look at today, is the number of ways of choosing an object from a collection of disjoint sets is just a sum of all of the number of elements in the individual sets. So here's example 2. I have a costume trunk that contains only red masks, green masks, and yellow masks. And we're told that there are 2 red masks and 5 green masks. And that there are a total of 10 masks. But it only has red, green, and yellow masks. How many yellow masks have to be yellow? Well, since we know that the total number of masks is 10, and we've already accounted for 7 masks, there have to be 3 yellow masks. That is, by the addition law, 2 plus 5 plus x is equal to 10, where x is the number of yellow masks. And therefore, there are 3 yellow masks. So be careful. The addition law requires that the sets have to be disjoint. If we are working with overlapping sets, then we have to separate them into disjoint sets before we can apply the addition law. Here's an example of what I mean by that. I advise math and computer science majors. 15 of my advisees are math majors. 12 of my advisees are computer science majors. But 7 of my advisees are double majors in both math and computer science. How many students do I advise? So I have 15 math majors. And then I have 12 computer science advisees, but 7 of them have already been counted because they were double majors in both math and CS. And these count the 7 that are double majors. And so I can't just add 15 and 12 and 7, or even just 15 and 12. I have to identify that 7 of these advisees have been counted in both lists. And so the total is the number in this set, and I'll use color here to separate them out. There are 8 people who are math only. And then there are 7 in the overlap. And then there are 5 that are CS only. And 8 plus 7 and 5 gives me a total of 20. And so there are 20 students that I advise, because I can use the addition law here. I can add these numbers up because the red set and the blue set and the green set no longer overlap. I have separated them into disjoint sets. Since the set of math majors and the set of computer science majors are not disjoint, we can't use the addition law directly. Instead, we separate the students into 3 disjoint sets: those majoring only in math, only in computer science, and students majoring in both subjects. And then we know that the set that has of both majors has 7 students in it. So there are 8 students that are math majors only and 5 students that are CS majors only. These sets are disjoint, and so we can use the addition law on those 3 disjoint sets, and we get 20 students. Okay. All right. Here's a more complicated example. I have a tray of donuts where 9 are glazed, 6 are powdered, 4 have sprinkles. Some of them are glazed and have sprinkles. One of them is powdered and has sprinkles. No donuts are glazed and powdered. And there is a plain donut that lacks glaze, powder, and sprinkles. How many donuts are on the tray? So at this point, it might be more useful to make a Venn diagram of all of the different possibilities here. I'll call this set G for glaze, this set P for powdered, and this set for sprinkles. We're told that no donuts are glazed and powdered. So there are 0 donuts that are both glazed and powdered. But 2 donuts are glazed and have sprinkles. and one donut is powdered and has sprinkles. There are a total of 9 glazed donuts, and 2 of them have already been listed here. So there have to be 7 more here. There are 6 powdered donuts, and 1 of them has been listed here. So there's 5 more up here. 4 donuts have sprinkles, and 3 of them are already accounted for up here. So there is just 1 more that has sprinkles. And then there is 1 plain donut that is not in any of these circles. And so by the addition law, there are 7 plus 2 plus 5 plus 1. So 7 and 2 and 5 and 1. And then there are 2 more 1s. Plus 1 plus 1 equals, how many total donuts are there? 9 and 5 is 14, 15, 16, 17 donuts. Okay. We have identified disjoint sets, and now we can just add them together. Because we have separated, for example, the donuts with sprinkles into ones with sprinkles only, sprinkles and glaze, sprinkles and powder. And that separation was important here. All right. So let's look at the other case, the other law we're going to look at today. This is the multiplication law. This is for describing outcomes in which we have to describe more than one step in specifying an outcome. For example, in this example here, we're going to have to specify a color and a size in order to create a jacket. And we have 4 colors and we have 3 sizes. So how many different ways of ordering a jacket? If there are 4 different colors, maroon, orange, black, and white, and 3 sizes, medium, large, extra large, well, that gives me 12 different possible jackets. A maroon medium, an orange medium, a black medium, a white medium, maroon large, orange large, black large, white large, and so on and so forth. So, this case, I have told you the number of colors and I've told you the number of sizes, but they combine to form the individual outcomes. And so instead of adding 4 and 3, we multiply 4 and 3 to get the outcomes. The choices that we have to make here are not independent. They're not disjoint from each other. Orange overlaps with medium, large, and extra large. Black overlaps with the sizes. White overlaps with the sizes. And so we get 12 ways of being able to do this. This doesn't require disjoint sets. We are counting on these overlaps in this case. This is the multiplication law. If in order to specify an outcome requires making n choices, so in the example we were just looking at, specifying a jacket required making 2 choices, one for the color and one for the size. And these were the number of possibilities for the first choice, and these were the number of possibilities for the second choice, and so on and so forth. And each of these values is independent of the values that came before it. Then the number of possible outcomes is just a product of the number of choices you have at each level. This is theorem 2.5 in the book. Okay? So let's try a couple of multiplication examples. 2 standard 6-sided dice are rolled. One of the dice is green and one of the dice is red. So there are 6 possible results that we can get from the first dice. And then there are 6 possible results we can get from the second dice. And so we could have any number on the green dice, and any number on the red dice. And that gives me 6 times 6 is 36 possible results. I could say we get a 2 on the green dice and a 5 on the red dice, for example, or a 5 on the red dice and a 1 on the green dice, or, any of these combinations are possible. Okay? So we get 36 possible results. Let's look at a harder example now. T-shirt has shirts in 4 different sizes: small, medium, large, and extra large, and 8 colors: black, white, gray, blue, red, green, yellow, and brown. But the yellow and brown shirts only come in medium, large sizes only. How many different T-shirts do they carry? Okay. So there are 6 colors of shirts that are available in all 4 sizes, and 2 shirts that cover in just 2 sizes. So the choices are not independent of each other. If I have chosen a size first, then I might have 8 colors to choose from, or I might have 6 colors to choose from, depending on which size I chose. If I chose my color first, I might have 4 sizes to choose from, or only 2 sizes to choose from. So the choices are not independent of each other. But if we separate out the 2 special cases, the yellow and brown shirt, then we get 2 different sets of outcomes. So 6 colors of shirts are available in all 4 sizes, and so any number in the table, in the 6x4 table, is possible. We could choose 24 shirts that are black, white, gray, red, blue, or green. Yellow and brown only come in 2 sizes, so that forms a smaller table that only has 2 columns and 2 rows, and there are 4 ways of choosing a shirt, which is yellow or brown. These colors are disjoint from these colors, and since I have 2 disjoint sets of outcomes now, one that includes black, white, gray, blue, red, and green shirts, and one that includes yellow and brown shirts, the last thing I want to do is use the addition rule to add that 24 and the 20 and the 4 together. Since the set of black, white, gray, blue, red, and green shirts is disjoint from the set of yellow and brown shirts, we can use the addition law to get the total number of shirts. So there are 28 different kinds of shirts at this store. Okay. We had to do a little bit of work here to separate out cases where the number of choices were not independent, and then we had to then use the disjoint law to combine them back. Okay? So I'm going to wrap up for now. Let me describe 2 additional problems and have you think about them. We'll look at these later on and have you write up solutions to these. So, in this exercise, my home state issues license plates that consist of 3 letters, but not including I and O, which could be confused for 1 and 0 at high speeds. So, not using those letters, followed by either 3 or 4 digits. So, now in practical terms, some 3-letter combinations are not used due to them spelling something unfortunate, for example. But if we ignore that fact and just allow any 3 letters, not including I and O, and any 3 or 4 digit combination, how many possible plates can be issued in my state? And then for the second exercise, if we want to fly from Roanoke to New York City on American Airlines, we can fly nonstop, we can lay over in Charlotte, or we can lay over in Philadelphia. So those are 3 disjoint ways of being able to travel. And there's one nonstop flight There's one flight from Roanoke to Philadelphia. There are 5 flights from Roanoke to Charlotte. And then there are 9 connecting flights from Charlotte to New York, and then 3 connecting flights from Philadelphia to New York. How many total ways of there are buying a ticket from Roanoke to New York via American Airlines? I will mention that the data in this problem was correct a year ago, prior to the pandemic, but because of the flight restrictions and the social distancing restrictions and things like that, some of these flights are currently suspended. If you check the data now, there are a lot fewer ways of getting to New York than there used to be, but this used to be the case. So try these 2 exercises. If you have questions, let me know, and I'll see you again on Friday. Thanks for putting up with me. Have a good day.